Welcome back to Computer Science 3200. Today we are going to be talking about a very brief introduction to deep neural networks. Almost enough to sort of tell you what they are, but not get into any of the actual magic of them. So this should be a pretty quick lecture. And also, as a note, this is the last actual formal lecture of the class, which is nice. You know, all good things come to an end, but it's a bit sad that I won't be lecturing anymore for this class this term. I really enjoy this class. So for the remaining two lectures of the term, well, the designated lectures, the first one, I want you to go watch AlphaGo, the movie. So AlphaGo is here. It's on YouTube. So you can go watch that for free. It's an hour and a half long. So luckily it's about the same duration as a lecture. And there will be at least one question on the final exam related to AlphaGo, the movie. Okay. So you have to watch that. If you don't, then you're going to get one of the questions on the final wrong. So please watch that. And then for every one of my classes, I always sort of leave this emergency class available for whatever may happen. Sometimes during like a normal school year, there might be like a snow day or something like that. And so rather than just fill this with something arbitrary to keep the course going, you know what? You guys all have stuff to do. So take that last class to do whatever the hell you want. Go take a walk, work on your assignment, work on your project, whatever. So there's nothing here for the final lecture slot. So let's get started with the lecture on deep neural networks, shall we? And we'll end this course on a high note. Let's switch over here to the lecture slides. Okay, so lecture 19 is on deep neural networks and deep learning. Some resources really quickly. There's this really great book called The Deep Learning Book. It's for free online at this website. And also another great tutorial resource is Dive into Deep Learning at d2l.ai. So check those out if you're interested more in deep learning. And we will not be implementing anything related to deep learning or neural networks during this course, but there will be a question on the final exam related to neural networks and deep learning, okay? But the answer to the question will be in the slides. So you don't need to go study these deep learning books or any of that sort of thing. You don't need to go too deep into it. Anything that I ask during the final exam will either be in the slides or have been done during an assignment, okay? So, deep neural networks. A deep neural network is essentially a neural network that has a lot of hidden layers and a lot of neurons. However, they also have some extra processing. They've been very popular since Jeff Hinton and his team at U of T wrote their ImageNet paper in 2012, and they basically completely revitalized neural networks as an AI tool. And they went from, as I said before, almost not being used anymore to being the most popular form of AI that is done today. And that was really possible because of the rise of GPU computation power. So GPUs have hundreds, if not thousands of cores inside them, and all of these cores can do lots of floating point operations. And so you combine the structure of deep neural networks with the rise in GPU computation, and you get these extremely powerful techniques called deep neural networks. And they're going to combine multiple techniques which are effective in specific domains. And so before we talked about neural networks and how like you can just have a fully connected neural network, that's no longer the case with deep neural networks. Deep neural networks, how do I explain this? Someone who's like a deep neural network engineer these days is essentially in the business of tying together a bunch of techniques and the formation of the neural network in a way that best suits the given problem domain. And we'll see what I mean about that in a little bit. But deep neural networks are not just a big neural net that's fully connected. There are lots of different things going on inside a deep neural net. And depending on which techniques you are using inside the neural net, you're going to be good or bad at specific problem solving. All right. So again, one of the canonical example that of Geoffrey Hinton's 2012 paper was this ImageNet classifier. We talked about that in the last class, where their deep learning system was able to outperform by a large margin any pre-existing system for image classification. And one of the big things that went into that were called convolutions. So convolutional neural networks were the big success story of Geoffrey Hinton's paper. So what convolutions do, my face is a little bit in the way of this up here, but let me just show you real quick. Oh, no, that's locked. Okay. So convolutions, let's say we have some input image. And then now what we're going to have is, let's say we have a neuron that, for example, looks at a 3x3 pixel area of that image and produces an output. So over here, let's say this is our input image. So we have this two-dimensional input image. These cells over here are going to represent like the pixels in an image. And so what convolutions do essentially is they have this thing called a kernel. So up here, this is this 3x3 kernel, for example. This is called a kernel. And this kernel is going to apply some sort of transformation or operation to a smaller subset of the input image. And then that is going to produce an output image. So for example, this kernel is going to apply some operation to these 9 cells of the input image and then produce one value in a new output layer. And the next neuron is going to look at a small shift of that area. So this is best explained by actually looking at an animation. So here's what's happening. We have this thing over here, this 3x3 area is called a kernel. So let's say this blue area down here is your input image, okay? Then the input image is having this kernel applied to it, and then producing a smaller output image up here. So here it is on a smaller scale, here it is on a bit of a larger scale. And so that's called, this is the first step. When you hear of a convolutional neural network, these convolution kernels are applying some operator to turn this area of the original input image into a smaller area in a future layer. So what might one of those convolutional kernels look like? Well, one of them that's very popular is an edge detector kernel, okay? So what edge detector kernels are, essentially, they detect changes in an image. Now, this Sobel edge detector has been around forever. Like, since computers could store images, image processing has been using these edge detection kernels. And essentially, what these edge detection kernels do is they apply this operation right here in the X and the Y direction. And essentially what you're doing is you're detecting areas where values in the image change drastically, okay? So if we apply this kernel in the X and Y to this image, what we get is this image here, which is an edge detection image. So changes in the image are essentially edges in the image, right? So our brains are very good at edge detection. Because if we can detect edges, we can detect change, and we can detect the tiger that's running at us out in the savannah, right? So edge detection is something humans are very, very good at, and something you can do with a very simple operation like this. So you apply the kernel to the image, and then the output image is sort of the edge detected image. And so what you can do is you can use convolutional neural networks. Now, not all convolutional neural networks use edge detection necessarily, but many of them do. And they use this to group and detect features, okay? So here's what a deep neural net might look like. So for example, we have an input image, okay? So this input image, we're going to apply that convolutional kernel, which may do some edge detection. And what we get from these little, these like 3x3 areas over here in the image, once the kernel has been detected, are groups of these edges. So one edge might be like this on a slant, One edge might be straight up and down, one edge might be horizontal, and so we get this new edge-detected image. And then, as I said last time, what's happening in a neural network is that each new hidden layer detects patterns, essentially, in the previous layer. So if we have the first layer being the input image, and then the next layer being the edge version of that image, then the next one being patterns on edges, and then we have patterns on edges, what we see that each subsequent layer is detecting is maybe at first we just have these edges. Next we're seeing like, okay, maybe you can make out like a tire or like the front of a car, and then we're able to do like entire vehicle identification. So this is the very high level, hand wavy, abstract process that's going on inside of a convolutional neural network. Now, that's not all that happens. It's not just convolution and then fully connected network. There's other things happening as well. Another thing that happens is something called pooling. Okay? So in pooling, the output from the convolution is going to produce another matrix, right? So we take an image, we apply the convolutional kernel to it, and we get another matrix, which is some values. Maybe the edge detected image, for example. So then what you can do is let's take either the maximums or the minimums from an area in that matrix. And this process forms another matrix, and that process is called pooling. So essentially what you do, let's say we do this. So we have this image and we've detected edges. Now what we want to do is somehow highlight the most important edges in that image, right? So pooling can do this. So for example, over here, if I have this matrix, I'm going to apply some operation to it and like chop it up into like 2x2 sub areas. Then from each of these 2x2 sub areas, what I'm going to do is take the maximum value from each of those things. So up here, for example, I have 12, 20, 8, 12. And so the maximum value of this is 20 down here in the output matrix. Here, my maximum value is 112, so I put it here, 37 right here, and 30 up here, which you can't see because of my camera, but it's in the slides. So what this does is it sort of takes that output in a localized space and takes maximum so that we're highlighting the most important things in those areas. And then sometimes we repeat that process. So the convolution to max pooling process is repeated some number of times. Like some people do it up to 100 times, right? Just to really drive home, okay, these are the features that we really care about. And then we can optionally rerun the result of the output through another convolution and then another pooling. And the final output is run through a fully connected neural network. So deep neural nets have a lot more going on inside them than just a typical neural net. So it's not fair to say that deep neural nets are just big, fully connected networks. There are other things happening inside them as well. All right, so what we might see in a paper about deep learning is something like this. This is a diagram of how they actually formed the system for doing the learning in their task. So they have an input image, they do the convolutions, right? And then they do some pooling to produce new matrices of data or new images. And then they take those pooled images and they do convolution of that. And then they do pooling on that. And they repeat that some number of times. And then they have a fully connected network with the output either being like, this is a dog, this is a cat, this is a boat, this is a bird, right? Down here, here's just another diagram from another paper. And these are real neural networks that have been submitted in publications. And so this is the sort of way that you'd look at these diagrams. Now, this is not a new thing, okay? I know I said at the beginning that MIT was going to drop neural networks from its course because they hadn't done anything really interesting. That's not entirely fair, okay? So Yann LeCun and his lab have been doing this sort of thing since the 90s. So Yann LeCun is really the father of convolutional neural networks. And what he was doing back in the 90s was doing this for things like simpler image recognition or handwriting recognition. So they take an input, they do convolutions, then do some subsampling, pooling probably, then some convolutions, and then subsampling, and then a fully connected network on that. All right. So they were doing this on processors that at the time had like 100,000 transistors, and the number of pixels that were used during training, maybe they had a few megabytes of data on this, the NIST, this like handwritten numbers database that they had. And in 2012, an example paper, now we have GPUs with billions of transistors, and the number of pixels they used in the training was on the order of petabytes, right? So lots and lots of data, maybe not petabytes, maybe like tens of terabytes of pixels. So this has been around for a while. However, the recent successes that made this really take off are on the scale of the computation that can be done. Okay, so not fair to say that like Geoffrey Hinton invented this stuff, but he certainly made it more popular than it had been. And again, here's another example of image recognition and the type of neural network structure where you take convolution and then other operations such as, I think this convolution is edge detection, then ReLU is the activation function, and then more convolution, and you can see how many times they repeat this. And here's the pooling step, etc., etc. And this goes on and on and on. And you can eventually see that these patterns of patterns of patterns can actually identify things. So you can start to see faces, right? So here you might have like the third or fourth layer of the neural net where you start to see eyes and noses and stuff, and eventually you start to see faces. Then you may start to see, or things like elephants, elephants have these curvy features, maybe they have their tusks, and then the patterns on these features are actually the patterns of entire elephants, etc. And these can get very, very, very large. So convolutional neural networks, they can have millions and millions of weights that they use and lots of different steps. And so, as you can imagine, there is lots of computing required for deep neural nets. So these techniques are only recently really possible due to massively computing power. So GPUs have become ubiquitous, really, really cheap to manufacture, not so cheap to buy anymore. Thank you, cryptocurrencies. But what you're doing with GPUs is you're trading single processor speed for massive parallel processing, right? So whereas my computer's CPU might be like 4 gigahertz, right? My GPU may only be a few hundred megahertz, but there's 1,000 of those processors in the GPU, right? So 1,000 times 400 is way bigger than 4,000. And neural networks are inherently parallel, okay? So here's the CPU that you have. You might have a few cores. Now, modern day CPUs might have, up to 32 cores. However, you're still not having these like hundreds, if not thousands of cores inside a GPU. So GPUs still, for some problems, are able to solve them much faster than CPU. And what you have here is the reason that this is so parallelizable is that you can do the computation of the dot product for each neuron in parallel, right? So each neuron, you're multiplying the weights by the inputs, and then you're summing those. So you have, for example, all the weights times the inputs for this neuron, all the weights times the inputs for this neuron, then this one, then this one, then this one, then this one. You can do all of these calculations in parallel. You can do an entire layer in parallel if you want to. And so it really is a case, like it's a best case scenario. You're doing essentially dot products, which is addition and multiplication. And all of those things can be done in parallel, so it's massively parallelizable. So this was like the dream scenario for GPU computation. Okay. Autoencoding. Autoencoding is another thing that is done in some deep neural networks. So if you have some inputs, x1 to xn over here, what an autoencoder essentially is, now they may have different shapes than this, but you're going to have some input layer with n inputs. Then you're going to have a hidden layer of neurons, which is smaller than the input size. And then you have an output layer, which is the same size as the input size. So think about it this way. You have an input layer, which is of some large size. Then you have a hidden layer, which is of a smaller size, and then an output layer, which is the same size as the input. So you're taking large data, passing it through a small number of neurons, and then those neurons are trying to recreate the large data again. So what does this feel like to you? What would we call this outside of the neural network space? What is this process of taking big data, making it small, and then making it big again? Yeah, so this is essentially compressing. So you take some original input data and you use an autoencoder, and then the neural network is learning how to compress the data. And so what might your error be over here? Well, the error is just, does the output match the input? It's the simplest error function possible, because you're passing this through the neural net, you're getting a value out here with these weights and values, and then you get something like this. So here's an example of a little mite on a leaf, and you pass that through an autoencoder that has learned to compress it, and you get a compressed version of the image. Similarly down here, okay? So autoencoding sort of generalizes inputs, and it can be seen as a form of compression. And deep neural networks frequently use autoencoders. So unlike that sort of demo example, due to these sort of generalizations, it's sometimes really difficult to understand what the DNN is doing and exactly what features it's extracting. So these examples are sort of cherry-picked autoencoding. But because of the convolutions, the max pooling, the autoencoding, it's sometimes like not magic, it's just mathematics, but it's very difficult sometimes to just pick like a random point in the deep neural networks training and say sort of what it is doing, right? It's a complicated process, and one of the, how do I phrase this? One of the downsides of machine learning, especially with deep neural nets, is sort of the understandability of what's going on, right? It's like, why did the deep neural net produce this exact image? Well, because the weights happened to produce it, right? Because it had the minimum error in the training. It's a less explainable phenomenon than if we had written like, if this, then this, right? So there's a lot of research going on in the deep learning space to help the understandability or the explainability of what the deep neural networks are doing. All right, the next thing, dropout. What is dropout? So the curse of neural nets and a lot of problems are that it can get stuck in local maxima, okay? So what dropout does is it tries to learn in a more robust way. So with dropout, every iteration of learning, we're going to flip a coin for each neuron. And depending on the output of the coin flip, or the die roll, or whatever, we're going to enable or disable the neuron. On the next iteration, we're going to drop out a different set of neurons. And so what this does is it learns to encode the features in a way that it doesn't rely on a very specific neuron, right? So for example, if that neuron had been disabled somehow, this system doesn't completely crap itself, right? And if you think about it, that would be very good for us as well in our brains. Like if we had, I don't know, a cosmic ray hit one neuron, then all of a sudden we just shut down, that would be really bad. So this helps getting stuck in local maxima as well as overfitting to the training data. So this is what this looks like. If we have a fully connected network to start, each iteration of the training, we're going to turn off some of the neurons. So their outputs are essentially just zero. And so they are not contributing to the next layer in any way, shape, or form. Then on the next iteration, we're going to disable some different ones. And so dropout helps us learn more robustly by sort of spreading out the load or spreading out the responsibility of the neurons in the network. There's also this thing called drop connect, which is a generalized form of dropout. So dropout drops neurons, drop connect drops connections. And if we think of it, if we think about it for a second, drop connect is a superset of the functionality of dropout, because dropout can only do neurons, but if we drop all the connections to a neuron, then we have effectively disabled the neuron, right? But we could do drop connect and simulate like individual synapses being destroyed in the brain or something like that. Okay. So that is like my hand wavy way of saying what deep neural networks are. There's so much more to it than that, but it's not really worth going deeper in this course into it. But what I did want to do for a second was talk about deep reinforcement learning. So what we did in this course, especially with Q learning, was that we did what's called tabular reinforcement learning, okay? So tabular reinforcement learning has a discrete state representation. So we are at like X, Y in our state, for example. It typically has low dimensional data, and it has a state space that we can fit into a table, right? It's tabular reinforcement learning. We have a state action pair. We're able to create a table that has like QSA. So what we're going to do, if we want to apply reinforcement learning to larger and larger problems, like to image data, for example, because we can't possibly store a table of all possible images. So what we need to have is some sort of function approximation. So where we previously had Q of SA, so that's the value of doing action A at a state S, that is now going to be the result of a function, not a table lookup, okay? And it turns out deep neural nets are really, really good at function approximation. So enter deep Q networks. So deep Q networks, or DQN. So deep Q networks are networks that use deep convolutional neural networks for function approximation to approximate the optimal value of Q star. Okay? So what DQN essentially is at a high level, it's a modified version of Q learning that changes when some updates are performed. And this sentence is worded terribly. I don't know why I have this here. Essentially, DQN is a modified version of Q learning that uses a deep convolutional neural network to store the action values rather than a table. Okay, because tables get, the problems get big so fast we can't store them in tables. Tables are fine for blackjack, but they're not fine for StarCraft. And these were introduced in this paper, Human Level Control Through Deep Reinforcement Learning. And I'm not going to read this entire thing, but this is a section from the paper, okay, from that original DQN paper. And we can see over here, this is the update rule for the DQN network, okay? And look what we have over here as the target. We have the reward plus gamma times the max action at the next state that maximizes Q of SA at the next state and the next action minus the current value of QSA. What does that look like? This is essentially the tabular Q-learning update rule, but it's phrased in a way that now we're talking about errors in a neural network rather than a value in a table. Okay? So what they did was, in that paper, they used deep reinforcement learning to learn to play Atari. And this was really the first famous example of reinforcement learning in video games. So they had the input pixels of an Atari game. They passed that through a convolution, then through some other things, and then through another convolution, then through a fully connected network. And the output here was which inputs you should do at that state of the Atari game. So what they had was one output for every possible button combination on an Atari controller. So an Atari controller has 8 different directions and it has a button. And so what we have over here are all the possible inputs. So we have no input, we have all 8 directions, we have a single button press, or we have any of the 8 directions with the button being pressed. And so they were able to use DQN to learn to play Atari games pretty pretty well. A lot of them at a superhuman level and some of them at a not so superhuman level. In the next class, you're going to be watching the AlphaGo movie. And so AlphaGo used deep reinforcement learning to learn to play the game of Go. So this is just a screenshot from that movie. And AlphaGo combined deep learning with heuristic search. And I mentioned this before in the neural network lecture, but what they did for Go was they trained two different networks. They trained a value network, which means essentially, if you look at this board state, who's winning? Okay, so that's the value network, is how good is this state for a particular player. And they trained a policy network, which is, given this state of the board, what are some moves that I should consider doing? So I think you should do this move, or I think you should do this move or this move. So deep AlphaGo, jeez, I've lost all my words. AlphaGo initially started out by learning from hundreds of thousands of professional human replays. And essentially what it did was it learned the policy network, and input was the state, and the target was the move that the expert human performed. So their deep neural network, their deep learning scenario that they did was the policy network looked at all of these states of the game, and the input was the state of the game, the board, and the output was which move did the human make. And so what they were doing at first was essentially trying to mimic what an expert human player would do. Then they trained a value network, which was from all of these replays, okay? So let's say we're at this current state. What they learned was who eventually won the game from this state, right? So if someone eventually won the game, let's say the player with the white stones, let's say white won this game from this state, then it's probable that this state is good for the white player, right? Or if black had won, it's probable it's good for the black player. And so it learned through hundreds of thousands of replays a value network, which is essentially who won the game from that state. Once it had learned everything it could from humans, it started to play against itself. Then it continued to learn, it continued to get stronger, and it essentially played hundreds of years worth of Go per minute and ended up playing, I don't know, something like millions of years worth of Go in order to learn to play the game. So fortunately, humans are faster learners than deep learning, but unfortunately, humans can't play millions of games at a time. Okay, so in the end, it learned to play better than human professionals. AlphaGo 0 was the next version of AlphaGo, which was even stronger, and they learned entirely from self-play. So it uses Monte Carlo tree search, which is a version of heuristic search, or an algorithm within the heuristic search family to play games against itself. It learned which moves were good from self-play using deep reinforcement learning, and it actually converged faster and used less computation than the original AlphaGo. And it produced, like AlphaGo 0 is infinitely stronger than the world's best humans. Humans have no chance of ever winning a game against Alpha 0. And it worked really well for chess as well. And so here's a description that I'll leave in the slides. Self-play for reinforcement learning in AlphaGo. So they used Monte Carlo tree search over here. You can see the tree search, and then they learned which moves are good to do via deep reinforcement learning. And so they would select a move, they would expand the move and evaluate, and then back up the values. This is kind of standard Monte Carlo tree search stuff, but I won't get too deep into that. So Go has a very large branching factor. Humans have good abstractions of what moves to perform at a state. AlphaGo learned a policy network, and so that policy network essentially told it, okay, try these 2 or 3 different moves, and now it could narrow the heuristic search to only consider the moves in the policy network. And search also, as we saw from assignment 3, needs a good heuristic function to determine how good a state is, to like evaluate those things like the alpha beta that we did. And that's what they did. They learned that heuristic function from the value network. This, I feel like I've taught, I think I had all these slides at the end of the neural network lecture. Similar to the original version of AlphaGo, DeepStack, this poker AI from the University of Alberta, did the same sort of thing, except it used a deep counterfactual network and combined this with Monte Carlo tree search to produce a superhuman poker playing bot. Essentially saying that if you combine heuristic search and deep neural networks, you get really, really good results. So I would, if you have thousands and thousands of GPUs, try doing that. All right. Next, what does a deep neural network actually see? This is an important point I like to put at the end of the year to say that even though deep neural networks are good, they're still just mathematics. Okay? So, what do you see here? Do you see the same thing in these two images? Because it's possible that a deep neural network sees something completely different, right? So if you think what a deep neural network is doing, it's taking pixel values, it's doing convolutions, then it's adjusting weights, then it's just doing all of these matrix operations, right? So what researchers are doing now, well, this is actually several years old, but they're doing research into tricking deep neural networks. So what they did was this research took this input image, which was of a bus or of a, I don't know, what is this? A grouse or something like that. This is a temple. And they figured out some noise that they can add to the image that makes it look to a human to be the same image, but the pixel values were adjusted ever so perfectly so that the deep neural network thought that all of these things were an ostrich. Okay, so the deep neural network thought this was a bus. It added this noise to the pixel values, which to me looks like the same image, but to the neural net, they are different pixel values, right? So it thought that was an ostrich, that was an ostrich, and that was an ostrich. Same thing, these like hand sanitizer or soap dispensers, praying mantis, dog. Well, here's the image that makes it think it's an ostrich, right? Because it's literally just doing math behind the scenes. So some things that people have done in order to combat this, maybe they take the image and they first blur it a little bit to spread out that noise so it's not as important and it doesn't trick the DNN as much. But it's kind of shocking and scary how easy it is to trick some neural nets. For example, you can produce noise that makes things perfectly identify things as almost anything that you want, right? So you can take this actual image of a robin and produce so much noise that it's unidentifiable to a human, but the deep neural net thinks that this is a robin. It thinks that this is a cheetah, this is an armadillo, this is a panda. Or you can do things with the textures that make it believe that it's something as well. So for example, sometimes if you take like this, I think this was this Geoffrey Hinton's thing was this the original ImageNet paper that they tricked? But anyway, they produced these images from the same colors that were in the original image. So you can see here, this is kind of the same colors as a penguin. These may be the same colors as a starfish. You can kind of see the baseball pattern here or the guitar pattern here. But essentially, deep neural networks are not human, right? Now, I'm not saying humans are better. Deep neural networks are better than humans at some sort of identification. But they're an amazing feat of engineering. They produce spectacular results, but they're not magic. They're just mathematics, okay? So they're easy to fool if you try, and a lot of modern research is going into either trying to fool them or trying to not be fooled. Because if you're Tesla and you have deep neural nets looking at things and saying, okay, it's okay to run into this trash can instead of grandma, well, you better be sure that's a trash can and it's not grandma, right? So just be careful with your deep neural nets because they're not absolutely magic. All right, that's all I had on deep neural nets. I just kind of wanted you to give the flavor for it so you kind of know what they are, but you don't necessarily want to go implement them yourselves. And if you did want to go implement a neural network, you would not implement them from scratch. Okay, you would just go download TensorFlow or Torch or one of these other libraries that already exist, that you just go in and you sort of drag and drop all the pieces. So modern deep learning software, you would essentially go into their user interface and like click the input. You'd say the size of the input, then you'd in their UI, you'd go over and you'd click a convolutional layer and drag it in. You'd click a pooling layer and drag it in, et cetera, right? You wouldn't actually write it from scratch because you're never going to get to the point on your own that is nearly as fast as the implementation that they have or has nearly as many features. Like, there are hundreds of engineers at Google and at Facebook developing TensorFlow and Torch. You're not going to catch up to them. Now, if you want to implement one from scratch as a learning exercise, that's fine, but it's not going to have the same results as these modern things, right? It's almost like, okay, I want to use a computer for something, so I'm going to program my own operating system, right? Unless you're Linus, don't get your hopes up. All right, that's all I got. Go watch the AlphaGo movie, and then work on your project if you're a grad student, or work on your assignment and study for the exams. I had a really great time teaching this course. I'm going to be sending out on D2L a questionnaire, sort of a course evaluation that I write up every year. I really enjoy listening to your feedback, what you liked, what you didn't like, and I hope that when that goes out, if you think that I've done a good job in the course, tell me. If you don't think I've done a good job, tell me. Maybe I can improve it for next year. But I really enjoyed having you all here, and that's the last you'll see of my face until the exam. So good luck. The exam is on December 13th. It is in the engineering building, EN 2006, the big lecture hall, from 9 to 11 a.m. It's a 2-hour exam, but it shouldn't take more than an hour and a half to complete. It'll be very much like the midterm in terms of the difficulty and the types of questions that are being asked. Maybe I will do something on Discord where I talk about the exam, or no, I'll probably just release something on D2L, which gives some hints for the exam and stuff like that. Thank you all so much for people who are not in the course for tuning in and being a part of it and leaving nice comments. That was really awesome. We still have a lecture to do for my other course, so I'll see you in that one next week if you decide to tune in. So thank you very much, and I'll see you next year.